This is the CRJ200 Autopilot. It helps control the flight by managing altitude, speed, and direction, reducing the pilot's workload. A real panel would make this feel much more immersive, so let's build our own. In the last video, I designed the schematic for the control board. Now it's time to turn that schematic into a real PCB layout. Before jumping into the layout, let's quickly go over the most important components. This board mainly consists of an STM32F411 microcontroller and three 16-pin connectors that will link this board to the interface board. The placement of these connectors is critical because they need to align perfectly with the rest of the system. I also have a simple 2-pin header for power input and a few supporting components like capacitors and resistors. The first step is setting up the board. I need to define the outline to make sure it fits properly inside the panel. I'm keeping it compact but making sure there's enough space for all the components. Since this is a control board, I don't need a super complex shape and layout. A rectangular layout works fine, but I'll round the corners a bit to make it cleaner. Now that the board outline is ready, let's start placing components. Before placing any components, I always start with the connectors. Why? Because they determine how the board interfaces with the rest of the system. If they're misaligned, the whole design is useless. So always double-check connector placement first before moving on to anything else. When placing components, think about routing in advance. If you randomly drop parts on the board without planning, you might end up with a maze of tangled traces. To avoid this, place components in a way that minimizes crossings and keeps signal paths as direct as possible. With all the components in place, it's time to start routing, or in simple terms, wiring up the circuit. For the signal lines, I'll try to keep them as short and direct as possible to avoid interference. Let's start by connecting the microcontroller to the 16-pin connectors. These traces need to be clean and avoid crossing each other too much. Since I'm using a 2-layer board, I may need to use vias to jump between layers when routing signals. I'll try to minimize the number of vias to keep manufacturing simple and costs low. Vias help connect different layers of the PCB, but their placement matters. If a via is too close to a pad, it can cause soldering issues. If it's placed incorrectly, it can increase signal impedance. Keep vias clear of sensitive areas and use them strategically. One common mistake is using traces that are too thin for power lines. A thin trace carrying too much current will heat up and could fail. A good rule of thumb: for every amp of current, use at least 1 millimeter of trace width. When in doubt, make them thicker. Once all the signals are connected, I'll do a quick check to make sure there are no cross traces or overlapping connections. The Design Rule Check, DRC, helps me spot any errors before I send this for manufacturing. Alright, let's run a quick DRC check before finalizing the layout. And oops! We've got 3 violations where traces are too close to vias. Let's take a closer look. Here's the issue. These traces are too close to these vias. This could cause manufacturing problems or even electrical shorts if soldering isn't perfect. Fixing this is simple. I just need to adjust the trace spacing to meet the design rules. A good practice is to keep at least 0.2 millimeters of clearance, or more, depending on the manufacturer's guidelines. Now let's rerun the DRC check and we're all clear. That's why you always check before sending your PCB for fabrication. These small fixes can save you a lot of time and money. One small clearance issue can ruin your PCB, so always double-check your design before manufacturing. If you're designing a PCB, don't forget to add a solid ground plane. It reduces noise, improves signal integrity, and makes routing easier. Without it, you might run into signal issues or electromagnetic interference. Just remember to keep signal return paths short. Now for the fun part, let's check the 3D view. Before finalizing your PCB, check the 3D view. It helps you catch issues like misaligned connectors, clearance problems, or component overlap. A quick 3D check now can save hours of frustration later. This lets me see what the board will look like once it's manufactured. Everything looks good. The connectors are aligned, the microcontroller is placed well, and all the traces are clean. Seeing it like this makes it feel one step closer to reality. That's it for the PCB layout. In the next step, I'll get this board manufactured and tested. Once I receive the board, I'll solder all the components and see if everything works as expected. If you're enjoying this project, let me know in the comments. Also, if you have any suggestions or improvements, I'd love to hear them. See you in the next one.